All right, so whoops. Today we're going to be moving on and continuing with our functions unit. So let me get this started. There is a video posted that you should watch before this that will teach you how to use the graphing calculators. I don't have a good way to display them on my computer screen, so I figured that one's going to be a little bit more clear for you guys. If you have questions about that, you can ask me during class tomorrow or today, or I guess it'll be today when you're watching this video. But anyway, we're going to talk about functions, getting on to different types of representations of functions. So let's get started. So there are many different ways to represent a function. So far, we have mostly talked about the symbolic representation or the math equations that represent a function. Those are the kinds that you're probably the most familiar with, but some other types of representations include graphical representations, numerical representations, and verbal representations. Graphical ones, I'm sure you guys have all seen plenty of times. You will continue to work with them throughout this class. Numerical ones are helpful for making those graphs, and you've definitely seen tables of numbers as well. Verbal representations might be a little bit new, but they're generally speaking just kind of a way of describing how the function works. We'll talk about it in a little bit more detail in just a minute. So graphical representations are the first ones we want to talk about. And graphical representations are just graphs that represent all of the points or coordinate pairs that exist within a function. Here's a bunch of examples of different graphs. Now, not all of these graphs are functions. There are three that are not actually functions. And while I'm talking, try to identify those. I'll talk about it just in a second at the end of this. But graphs are a visual way to represent all of the combinations of inputs and outputs in a function. So remember that we think of functions as x being our input, y being our output. So let's say I want to do an x value of 1 on this graph. I would come here and go up to my output, which looks like it's about 4. None of these are numbered, so it's hard to say. So input is on the x-axis and the output is on the y. Graphing calculators, which again, if you watch that first video first, you should already know how to do this now, or at least have an idea of how to do this. You'll get some practice throughout the next couple of weeks, and we'll use those graphing calculators a lot more later in the term. But graphing calculators can allow you to graph a function from its symbolic representation. So just directly putting in that equation, it'll automatically graph it for you. Normally, what you would do if you're trying to, oh, by the way, the 3 on here that are not actually functions are C, D, and E, all of which would fail a vertical line test. But normally, the way that you would graph a symbolic representation by hand is to first draw out a numerical representation. Numerical representations are just tables showing various values of the inputs, x, and the outputs, y, of a function. Note that this kind of representation rarely contains all possible inputs and outputs. The only time that this can contain all the possible ones are when you're dealing with something that can only be whole integers. You can't write, obviously, all of the decimal points that would be in between integers, so it only works in real-life functions where something has to be a whole number every time. And that's not terribly relevant to what we're doing right now. But numerical representations are good for highlighting some key points on a function. So things like the y-intercept, the x-intercepts, any maximums or minimums, any place where the slope is the greatest, stuff like that. Generally, when creating a numerical representation, you want to include as many important points as possible. So like I said, those y-intercepts, x-intercepts, all that kind of stuff. Here's one example of a numerical representation. You've got your x on the top, and then we just chose some random points. I did -2, -1, 0, 1, and 2. And then the f of x is listed below that. In this case, we have f of x equals x squared. So we get 4 for -2. When x is -2, we get 4 for f of x. When x is -1, we get 1, 0, we get 0, 1, we get 1, and 2, we get 4. And then this is another type. You can do them vertical or horizontal. It doesn't really matter. It's probably easier to write in your spirals if you do it horizontal, but you'll probably more often see data tables written out more like the bottom one. And so in this case, f of x is 3x plus 1. So when x is -2, f of x is -5, x is -1, f of x is -2, and so on and so forth. Verbal representations, the ones that you have probably seen the least. These are the ones that are probably also going to be the weirdest to actually present, because this is not a way that people generally speak. It's kind of awkward in non-real life terms, but we'll look at a real life example at the end here too. So verbal representations are just the words that describe a function. An example of a verbal representation of f of x equals x squared might be something along the lines of take the square of the input to get the output. And remember, when we're talking inputs and outputs, input refers to x and output refers to y or f of x. If we're using function notation, it's f of x. If you're using standard notation, things you might be more familiar with, the output is y. These types of representations are mostly used for very practical functions. So for instance, the one that I'm about to show you is an example of buying apples. So in this case, A is used to represent the apples because those are our output. And in this case, dollar signs, which are going to represent the number of dollar bills we put in, represent dollars. So in this case, this function basically says that for every $1 I put in, I get $3 out. So the way you might say this in a verbal representation is multiply the input by 3 to get the output. But in this case, remember, if we have our input and output machine, we put in $1 as our input, we get out 3 apples as our output. So here's an example where we're going to go through all 3. So we want to write the numerical, graphical, and verbal representation of the function f of x equals 2x minus 4. It's almost always easiest to start out with either the verbal or the numerical. When you're doing the graphical one, unless you're using a calculator, it's going to be easiest to have the numerical values ready. So let's start with numerical. We're going to pick some random points. It doesn't really matter in this case. We're going to take -2, -1, 0, 1, and 2. The reason I keep using those is actually because that's what's going to be on your homework. It's going to ask you to do that in a couple of problems with specifically those points. So then when we do our f of x, we're just plugging in those numbers. So the first time you do x -2 or f of -2 equals 2 times -2, which is -4, minus 4, which is -8. And then you'd have f of -1 is 2 times -1 minus 4, which is -6, and -4, and then -2, and then 0. Then when we're graphing, we need our nice little graph paper here. These points are going to be slightly off because I actually put them in by hand. But first off, it's easiest to graph our points. So those are the points we just made in our numerical list over here. We graph them right on this graph, and then we can just draw a line straight through them. And yeah, graphing, especially linear functions, is pretty simple, and you guys have probably done it a decent number of times. Now, the verbal representation is going to be a little bit weirder. Once again, you kind of have to, think around how you would describe this function to somebody who's not used to math. So in this case, it's double the input and subtract 4 in order to obtain the output. Right, so this 2x, we're doubling whatever our input is x, and then subtracting 4 to get our f of x or our y. And that is actually all we've got in this lecture today. So hopefully that should be enough combined with the graphing calculator thing. The main thing you're still going to need to know or still be able to do is write out those domains and ranges as or in interval notation. So if you need more practice with that, I'd be happy to help you during class. We can hang around and talk about it. But hopefully this isn't too complicated for you guys just yet. The next part, I believe, is the last part that's mostly review. And then after that, we should be getting into some new material for everybody. So that is it for today, and I will see you guys later.